Hello, Gen Chem Tribe. Today we are talking about kinetics. And so we're basically getting into rates of reaction. And so basically we're just looking at how fast or how slow a reaction proceeds. So we have some kind of new, notation to look at. We're going to see a lot of this idea of brackets and a molecule within the brackets. So the brackets actually mean something specific, where it means that we're talking about a concentration. And so we'd be looking at, molarity, or a pressure. And generally will be in terms of atmospheres for that. So that's some shorthand, and we could, in terms of the basic idea of a rate, is really just a change over a change, meaning, with miles per hour, the change in miles over the change in time. And that's what we see here with this basic understanding of rate, that we could look at the change in concentration or the change in pressure over a change in time. So that's the beginning idea of rates, right? That we could just kind of just look at how fast something disappears over time or how fast something appears over time, depending if we're talking about starting material or product, respectively. Our time could be, lots of different units. So it really just depends on, how fast or how slow the reaction is. We have a very fast reaction, we tend to be in terms of seconds. A very slow reaction might be in terms of days or possibly even years. So if we were to look at like a simple reaction of hydrogen gas plus bromine gas to produce hydrobromic acid in the gaseous state, we could measure the rate of disappearance of our starting materials. Or we could look at the rate of formation of product. Well, it's just a really just general way of looking at the rate. So if we kind of just looked at an average rate, we could look at the average rate of hydrogen consumption. And that would be just looking at, that change that we have the average rate would be the change in concentration or pressure of hydrogen gas over a change in time. So that would be with regards to the one starting material, the hydrogen gas. But we could put it really into terms of all the materials specifically. Looking at the consumption of bromine over time, or production in terms of our products. So, this is somewhat specific, in terms of, okay, which specific starting material am I looking at? Which specific product am I looking at? So, again, that's just looking at that very general reaction of hydrogen plus bromine to produce hydrobromic acid. Now, if we were to look at plots of these, what we would see really just, very much the same, but really depends on whether we're talking about, a starting material or whether we're talking about a product being produced. And so we could have time on the x-axis, and then we could have, our concentration or pressure in the y-axis. And so I have this broken down here, as you can see, into terms of starting materials on the left and products on the right. If we were to look at a plot of the consumption of starting materials, starting from time, 0, we're going to have a very high concentration of starting materials, right? Because that's what we're beginning with. And what we would notice over time is that we have this curve that is decreasing over time. And then it tends to flatten out. And so this would be, the rate of consumption. And then if we were to coordinate some data points, right, we could actually look at the slope of our line. And what is the slope? Well, the slope is the rate. So here, looking at a delta in terms of the change in concentration over the change in time. And what we can see is that there is a flattening out of this as we go. So here, our slope would be equal to the change in pressure or concentration of my starting material over the change in time. And what do we notice is we, observe a fast rate of reaction at the beginning, but this rate slows down over time. And hopefully that makes sense. This talks about probabilities, that, the idea is that over time, there is less of a probability of starting materials interacting to produce product. Right? And that's just because as we go, we make more and more product. And so now it becomes harder and harder for the starting materials to, if you will, run into one another and then react. And so we see this common decrease in the actual slope. In terms of our product, it's really the exact opposite. We would be starting at 0. And we would see, initially a very fast rate of reaction. But over time, that rate would actually slow down. Again, if these are tied to one another as far as our starting materials and our products. And so we find that not only do we see a decrease in rate of consumption of the starting materials, but we also then see a decrease in the rate of our product production over time. And so realize that this slope is equal to the rate. However, that means that if we consider the rate of certain materials is going to be faster or slower than others. So, for instance, the rate of HBr production this will be 2 times faster than H2 or Br2 consumption. And this is simply due to the reaction stoichiometry. Meaning that if we consider the stoichiometry, we're looking at H2 plus Br2 produces 2 HBr. So 1 molecule of H2 disappears, but 2 molecules of HBr appears. And so that means that we have different rates for different materials. So the rate of a reaction for a specific or particular starting material or product is dependent on its stoichiometry. However, these molecules are part of the same reaction. So, we need a way to, to relate rates of reaction with respect to starting materials or product to the overall rate of reaction. So we need to bring in some stoichiometry into the mix. So if we consider our reaction that we were talking about, there's a couple things that we need to do. So if we talk about just the overall rate of reaction, we could say, well, that is equal to the change in concentration of hydrogen over the change in time. But realize that we have a negative slope here. And if you think about rate in terms of speed, it doesn't make sense to have a negative velocity. Like I want negative 10 miles per hour. You would have to have something positive. So we would want to have a negative sign out in front. And so the negative sign here corrects basically for the negative slope in the consumption of starting materials. And so that would be very much the same as saying, whether we say it in terms of BR or whether we say it in terms of BR2. Right, again, we have that negative sign as a result of that negative slope that we get. If we consider that in terms of the product, we now see something, else going on here. There's no need for sign change since there is a, positive slope. For the product production. But need to account for the stoichiometry. Right, HBr is produced 2 times faster, so we multiply by 1/2, so all rates are 1 to 1 to 1, etc. So we have that idea of stoichiometry playing a part as well. So as an example of this, we could say that the overall rate of reaction for the following process is 3.00 molar per second. What is the rate of consumption of N2O as well as the rate of production of nitrogen gas. And we have our reaction here with our nitric oxide producing nitrogen gas and O2 gas. We find that the overall rate is equal to 3 molar per second. So if we look at part A, for part A we're looking at the rate of consumption of N2O. So if we look at A, we would say, well, the rate of the rate of N2O consumption would equal 1/2 times our delta N2O over our change in time. And so our rate, as well as, I apologize, remember that negative sign out in front. So we have our negative to correct slope. We also have our stoichiometry rate correction. So we know our rate is 3 overall, and so that must equal 1/2 our delta N2O over our delta T. And what we want to find is that rate of consumption. Right? Our rate of consumption here is what we find within the brackets. Right? It's just that this front piece is just correcting for how that relates to the overall rate of the process. So if we would take our 3 molar per second, we are then multiplying that by -2 by bringing over the -1/2. We find that our rate of the N2O gas consumption, which is equal to our change in its concentration over our change in time, would be equal to a negative 6.0 molar per second. This is a starting material, so we should have a negative slope, which we do, and do the stoichiometry, we should have that rate multiplied by a 2 value to accommodate the stoichiometry. So that would be the rate of N2O consumption. For part B, we're looking at the rate of production of the nitrogen gas. We still have the same overall rate, of course, because it's the same reaction. So for part B, we're looking for the rate of N2 production. And so that would be equal to plus 1/2 times our change in concentration of nitrogen over our change in time. Right, that's how that responds to the overall rate of nitrogen production is in this piece of the rate expression, but we have to relate that to the general rate that we have. So here, there's no need to change the sign of the slope. We still have this stoichiometric or stoichiometry rate correction, and those are both then equal to the rate of our particular process. So we would say that our rate, again, overall was 3 molar per second. In terms of relating it to our product, specifically the nitrogen gas product, we would set it equal to this expression. So very much similar to what we did before, right? We multiply over the 2, and then that's going to be equal to our change in concentration over our change in time, specifically for the nitrogen gas, and that would be equal to 6.0 molar per second. So that's how we can look at general rate expressions, very simplistically here, in terms of generally change in concentration or change in pressure over a change in time. We can relate these specifically to starting materials or products, or we can also put them together and relate them to the overall rate of the reaction. And so applying them to the overall rate of the reaction, we have to take into account, if it's a starting material, we have to apply a negative sign to correct for the slope. If it's a product, we don't need to do that particular step. If there is stoichiometry higher than 1, then we also have to correct for that so that all of these materials are on the same playing field. And that's the notion of just simple general rates of reaction. We also have what's known as rate expressions. And rate expressions are basically a way to detail how a reaction how a reaction's rate proceeds with time. So our rate expressions here are always in terms of starting materials. So, to be honest, we start with our starting materials. It's easy just to watch their consumption over time, and so we can basically just kind of really apply this rate expression, a way to look at a reaction in terms of time, in terms of just the actual starting materials. So we have like a general reaction, say something that looks like this. Right, we could write this rate expression in terms of, okay, our rate is equal to little k times the concentration of our starting materials raised to the x power. So here we have our rate of reaction. Little k is known as our rate constant, for the reaction. This is very specific to each and every reaction. This is temperature dependent, but it is pressure or concentration independent. We tend to see our units here of K being in terms of reciprocal time. We then, on the other side, we have our concentration, or we have our pressure of starting material A. And then we have what's known as reaction order. With respect to A. And so reaction order is, how dependent rate is on the concentration or the pressure of A. So we might find that it's more dependent or less dependent, and that depends on our X value. So with these, we can start with a number of ordered processes. We could look at a zero order reaction. That means that our X value is going to be 0. And if we're looking at our general reaction like we have above, that means that the rate of the reaction would equal little k times A to now the 0 power, right? And so there is our reaction order, and this is a 0 order process. If we were to look at a plot of, let's say, rate versus concentration of A, we would basically end up here with a straight line. Because if you think about it, well, anything raised to the 0 power is 1, so in this case, really K is equal to the rate, so we would expect a flat line. Phase changes, such as sublimation, are examples of 0 order processes. So there's a 0 order reaction, right? This is just a particular reaction that just is independent on the concentration of starting material. So if we think about sublimation and think about like dry ice, dry ice naturally sublimes at, our normal pressure of, 1 atmosphere and 25 degrees Celsius. So, but it doesn't matter if I have a big brick of CO2 or a small granule of CO2, they actually sublime at the same rate. It's independent on how much of that material I have, because of this idea of phase change, as well as the idea that this is just a 0 order process. And there are many types of rates, or many types of orders of reaction. We tend to focus on 3 of them: 0 order, first order, and second order. So if we look at a first order reaction, Now our x value is going to equal 1. So if we're looking at our conversion of A to products, our rate would be equal to little k times the concentration of A raised to the first power. So here is where we would have a linear relationship between our concentration or pressure of A and the rate of our reaction. So if we have same type of plot of rate here versus concentration, that concentration or pressure of A, we would get a straight line like this. That if there's low concentration of A, such as no A, well then we don't have a rate. But as we increase the concentration of A, we see an increase in the actual rate of the process. This is a first order process. This is a linear relationship between the two. The third relationship, like I said, there's many order processes out there. But for us, we just do 0 order, first order, and now a second order reaction where now x is equal to 2. And we can do the same analogy that we have A going to our products, and now our rate is equal to little k times the concentration of A to the second power, or squared. So there is our second order. In terms of the square, just like above, we had our first order. And so here we have a now exponential relationship. Between the rates of reaction and our concentration of A. So now we just find even more of a dependence with a second order type process. So if we do the same plot of rate versus concentration, we now end up with this exponential curve like we see here, that it exponentially increases with increasing starting material concentration. In terms of rate expressions with more than one starting material, it's just, kind of tacking on the other starting materials as we go. So if we had, let's say, molecule A plus molecule B goes to our products, here again we have our stoichiometry, which is not important to order or anything like that. And then here we have our molecule A and our molecule B, right? Our rate would be equal to little k times the concentration of A raised to the x power, and that was very similar to what we saw when we just had A as a starting material, but now we have B, and it's going to be raised to the Y power. So, rates in terms of the starting materials is multiplicative, right? We're not adding or subtracting. X here is the reaction order with respect to molecule A, while Y is the reaction order with respect to molecule B. So those are just now, and they don't have to be the same. They could be different, right? Because it's just really talking about the reaction rate on and its dependence on one starting material or another. So while we have X is the reaction order with respect to A and Y is the reaction order with respect to B, we also have then overall reaction order, which is basically the sum of the individual orders. So that's our idea of rate expressions. In terms of we always have a very general expression of rate is equal to K times our starting materials, and then those starting materials are raised to a specific order. We find that we can have zero order, first order, second order. We can have multiple different types of orders with respect to a starting material and the actual rate of a reaction. Now let's look at how we can determine it. How can we determine our overall rate expression with an actual experiment? And so we're going to here use an example to put together a method for solving rate expressions. From actual data. So our example here would be for the following reaction, and our reaction would be looking at 2A plus 3B goes on to produce some products. The following data was acquired. And here we have, our concentration of A. This is going to be in terms of molarity. We have our concentration of B, also in terms of molarity. And then we have just our general rate. And so we have a number of different trials where we start with, concentration of 1 molar and 1 molar. And we end up with a rate of 1.24 times 10 to the negative third. We then increase the concentration of both of our starting materials to 2 molar, and we end up with 3.5 times 10 to the negative third for our rate. And then in the third trial, we keep A the same, but we change B to 4 molar, and we get a rate of 7.05 times 10 to the negative third for our rate. And so we want to basically determine our reaction order with respect to A and to B. Part B is asking us the overall reaction order. And then part C is asking us to determine or calculate the rate constant, little k. So there's our different pieces that we have to do. So the first step is to write the rate expression in terms of the starting materials. So if we look at our reaction, we had 2A plus 3B goes to produce products. So that means our rate for the reaction would be equal to little k times A to the x power times B to the y power. And again, remember, stoichiometry is not important in these rate expressions. It was important for general rates of reaction like we talked about earlier, but they are not important in these rate expressions. So there is our rate expression in terms of A and B as well as then X and Y. And what we need to do in part A is figure out what X and Y are. So we need to determine what X and Y are within our rate expression. Step 2 is to set up a ratio of rates from different trials, making sure, and this is really important, making sure that only one starting material is changing in terms of concentration or in terms of pressure. This is very important since we have multiple unknowns. Namely, we don't know what little k is, we don't know what x is, we don't know what y is. The ratio helps simplify but also to know how rate is affected by a particular starting material, we have to make sure it is the only thing changing. Right? In an experiment, or scientists are doing an experiment, if I change multiple things and going from one experiment to the other, I can't say whether what I changed had an impact on the reaction because I changed multiple items. To be, a scientist, we want to change really only one thing at a time. So that if I just change one concentration and my rate slows down, well, then I know that my rate decrease is due to that change in concentration. Or if I increase the concentration of only one starting material and I see an increase in rate, well, then I can ascribe that increase in rate to that one starting material. But if I'm changing multiple starting materials, then I really can't do that. So if I look back to my experimental data, I really want to compare trials 2 and trials 3 because only the concentration of B is changing. Right? A is staying constant, but B is changing. And so I can ascribe the rate increase, which I see, in going from 3.5 to the negative third to 7.05 to negative third. Right? That rate increase is solely dependent on B because that's the only thing I'm changing. I'm keeping the concentration of A constant. So trials 2 and 3 are where we would begin. So if we then say, okay, what do I want to do? I want to do a ratio of my rates. So I would say, okay, well, the rate of trial 3 over the rate of trial 2. Well, what does the trial, rate 3 equal to? Well, that's just kind of using, what we had talked about before, that the rate is equal to little k times the concentration of A to the x power times the concentration of B to the y. And we could be a little more specific if we just want to put, that those concentrations would be from the third trial. What's the rate of 2 equal to? Well, that's equal to k times A to the x times B to the y as well. What those would then be for the second trial. So the ratio of rates allows for one unknown, namely k, to cancel out. K, remember, is equal to our rate constant, and it is a constant for this reaction. So that means that our K value and our K value can fall out because of that ratio of rate. So again, that's one reason why we set up the ratio, is so that it helps to simplify the process. And so now what we want to do is now substitute in values from the table and solve for one of the orders. The other should drop out since the concentration is not changing. For one of the starting materials. So if we go up to the top and we start to plug things in, our rate for the third process was 7.05 times 10 to the negative third. The rate for the first process was 3.5 times 10 to the negative third. Or I'm sorry, for the second process, 3.5 times 10 to the negative third. Our concentration of A was equal to 2 molar, and our concentration of B was equal to 4 molar for that trial 3. That would be over then the concentrations from trial 2. Where we have 2 molar for our A, and we have 2 molar for our B. And so there's trial 2. And so notice we find that our 2 to the x and 2 to the x cancels out. Again, this is why we pick 2 trials where only one starting material is changing, right? And so now that simplifies. We had 3 unknowns, little k, which already dropped out. We have x and y, and now x has dropped out. And so we find our rate, or our ratio of rates, is equal to 4 to the y over 2 to the y. And if we go, one step further, we could say that, roughly 2 is equal to 2 to the y. Now, obviously, this is an easy one to figure out, but how can we pull out that y value? We want to use log to solve for the power, or solve for, rather, reaction order. Remember, if you take the log of something raised to a power, then that power comes out in front. So the log of 2 would be equal to y times the log of 2. Or y is equal to the log of 2 over the log of 2, or y is equal to 1. So we know here that our reaction order with respect to B is first order as a result. And so basically now we repeat the process to solve for the other order. Since there's only one left, we can pick any 2 trials. So in this case, I picked trial 2 and trial 1. So we kind of repeat the whole process. We want to set up a ratio of rates, and we want to simplify. So we would have our rate of 2 over our rate of 1. There's our ratio of rates. Our rate expression is equal to K times the concentration of A to the X times the concentration of B to the first order, right? We already know that. And that will be over our other rate expression, which is exactly the same thing, right? We just have different trials that we're plugging in as far as trial 2 or trial 1. K cancels out, since this is a constant. For this reaction. And so we end up with the rate of 2 over the rate of 1 is equal to the concentration of A to the X power times the concentration of B to the first power for the second trials over the same process, A to the X, B to the first for the first trial that we have. So now we substitute our values in from the trials and solve for our reaction order. So if we start to plug in those rates, we had a rate for trial 2 to be 3.5 times 10 to the negative third over 1, which is 1.24 times 10 to the negative third, is equal to our concentration of A for that second trial, which was 2 molar. B was also 2 molar. And that was for the second trials. And then for the first trial, both of these were 1 molar. And so if we now start to solve this, right, we get a value of 2.822 for our ratio. And that would be times 2 to the X times 2 in terms of breaking that fraction down. If we collect like terms, right, we would have 1.411 is equal to 2 to the X. Here is where we use log to solve now for reaction order. So we want to take now the log of both sides, and that's how we get the X value out in front of the material. And so if we solve for that, right, our X is going to be equal to the log of 1.411 over the log of 2, and we get a value of 0.497, which is really right on the money with 0.5. So the reaction order with respect to molecule A is half order. You can see half order, but that is it in terms of fractions. If you get something off, more than likely we have a miscalc. So normally order is equal to 0, 1, 2, 3, etc. And also, possibly 1/2. So we can have half order processes. Generally, we see these integers such as 0, 1, 2, and sometimes higher levels, 3, etc. But we do have the possibility of half order. So for part A, our reaction order with respect to molecule B is first order. And our reaction order with respect to A is 1/2 or half order. The overall order would be equal to X plus Y. And so we would have 1 plus 1/2 or 1.5 as our overall order for the process. So we have our B being first order, we have our A being half order, and then we put those together, and that gives us 1.5 overall order. For C, we have to solve for K. And so now that we know orders, we just pick a trial, substitute in the values, and solve for our little k. So at this point, our rate would be equal to little k times the concentration of A to the 1/2 order times the concentration of B to the first order. So there's our rate expression so far. I'm going to pick trial number 2. And so that's what I'm plugging in below here, that we have our rate of 3.5 times 10 to the negative third is equal to little k times the concentration of A, which is 2, raised to the 1/2 power, times the concentration of B, which is also 2, raised to the first power. And so my little k would then be equal by dividing over my 2 and my 2 raised to the 1/2, I get a rate constant equal to 1.23 times 10 to the negative third reciprocal seconds in this case, in terms of time, right? So there is our rate constant. And so that means our rate expression is equal to, rate is equal to little k. What is our little k? Well, it's 1.23 times 10 to the negative third reciprocal seconds times the concentration of A to the 1/2 times the concentration of B to the first order. And that is now our overall rate expression derived from the experimental data.